Newton's law of universal gravitation states that any two bodies in the universe attract each other with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. Separately, it was shown that large spherically symmetrical masses attract and are attracted as if all their mass were concentrated at their centers. This is a general physical law derived from empirical observations by what Isaac Newton called induction. It is a part of classical mechanics, and was formulated in Newton's work Philosophiæ Naturalis Principia Mathematica, the Principia first published on the 5th of July, 1687. When Newton's book was presented in 1686 to the Royal Society, Robert Hooke made a claim that Newton had obtained the inverse square law from him. See History section, below. In modern language, the law states the following. Every point mass attracts every single other point mass by a force pointing along the line intersecting both points. The force is proportional to the product of the two masses, and inversely proportional to the square of the distance between them, where F is the force between the masses, G is the gravitational constant, M1 is the first mass, M2 is the second mass, and R is the distance between the centers of the masses. Assuming SI units, F is measured in newtons, and M1 and M2 in kilograms, kg, R in meters, and the constant G is approximately equal to 6.67410 and 11 nm2 kg2. The value of the constant G was first accurately determined from the results of the Cavendish experiment conducted by the British scientist Henry Cavendish in 1798, although Cavendish did not himself calculate a numerical value for G. This experiment was also the first test of Newton's theory of gravitation between masses in the laboratory. It took place 111 years after the publication of Newton's Principia, and 71 years after Newton's death, so none of Newton's calculations could use the value of G. Instead, he could only calculate a force relative to another force. Newton's law of gravitation resembles Coulomb's law of electrical forces, which is used to calculate the magnitude of electrical force between two charged bodies. Both are inverse square laws, in which force is inversely proportional to the square of the distance between the bodies. Coulomb's law has the product of two charges in place of the product of the masses, and the electrostatic constant in place of the gravitational constant. Newton's law has since been superseded by Einstein's theory of general relativity, but it continues to be used as an excellent approximation of the effects of gravity. Relativity is required only when there is a need for extreme precision, or when dealing with very strong gravitational fields, such as those found near extremely massive and dense objects, or at very close distances, such as Mercury's orbit around the Sun. Early history. A recent assessment by Ofergal about the early history of the inverse square law is that by the late 1660s the assumption of an inverse proportion between gravity and the square of distance was rather common, and had been advanced by a number of different people for different reasons. The same author does credit Hooke with a significant and even seminal contribution, but he treats Hooke's claim of priority on the inverse square point as uninteresting since several individuals besides Newton and Hooke had at least suggested it, and he points instead to the idea of compounding the celestial motions and the conversion of Newton's thinking away from centrifugal and towards centripetal force as Hooke's significant contributions. Plagiarism dispute. In 1686, when the first book of Newton's Principia was presented to the Royal Society, Robert Hooke accused Newton of plagiarism by claiming that he had taken from him the notion of the rule of the decrease of gravity being reciprocally as the squares of the distances from the center. At the same time, according to Edmund Halley's contemporary report, Hooke agreed that the demonstration of the curves generated thereby was wholly Newton's. In this way arose the question as to what, if anything, Newton owed to Hooke. This is a subject extensively discussed since that time, and on which some points still excite some controversy. Hooke's work and claims. Robert Hooke published his ideas about the system of the world in the 1660s when he read to the Royal Society on the 21st of March, 1666 a paper on gravity concerning the inflection of a direct motion into a curve by a supervening attractive principle, and he published them again in somewhat developed form in 1674 as an addition to an attempt to prove the motion of the Earth from observations. Hooke announced in 1674 that he planned to explain a system of the world differing in many particulars from any yet known, based on three suppositions: that all celestial bodies whatsoever have an attraction or gravitating power towards their own centers, and they do also attract all the other celestial bodies that are within the sphere of their activity; that all bodies whatsoever that are put into a direct and simple motion will so continue to move forward in a straight line till they are by some other effectual powers deflected and bent, and that these attractive powers are so much the more powerful in operating by how much the nearer the body wrought upon is to their own centers. Thus Hooke clearly postulated mutual attractions between the sun and planets, in a way that increased with nearness to the attracting body, together with a principle of linear inertia. Hooke's statements up to 1674 made no mention, however, that an inverse square law applies, or might apply, to these attractions. Hooke's gravitation was also not yet universal, though it approached universality more closely than previous hypotheses. He also did not provide accompanying evidence or mathematical demonstration on the latter two aspects. Hooke himself stated in 1674, "Now what these several degrees of attraction are I have not yet experimentally verified, and, as to his whole proposal, this I only hint at present, having myself many other things in hand which I would first complete, and therefore cannot so well attend it, i.e. prosecuting this inquiry." It was later on, in writing on the 6th of January, 1679 vertical bar 80 to Newton, that Hooke communicated his supposition that the attraction always is in a duplicate proportion to the distance from the center reciprocal, and consequently that the velocity will be in a subduplicate proportion to the attraction, and consequently, as Kepler supposes, reciprocal to the distance. The inference about the velocity was incorrect. Hooke's correspondence of 1679 to 1680 with Newton mentioned not only this inverse square supposition for the decline of attraction with increasing distance, but also, in Hooke's opening letter to Newton of the 24th of November, 1679, an approach of compounding the celestial motions of the planets of a direct motion by the tangent, and an attractive motion towards the central body. Newton's work and claims. Newton, faced in May 1686 with Hooke's claim on the inverse square law, denied that Hooke was to be credited as author of the idea. Among the reasons, Newton recalled that the idea had been discussed with Sir Christopher Wren previous to Hooke's 1679 letter. Newton also pointed out and acknowledged prior work of others, including Aldus, who suggested, but without demonstration, that there was an attractive force from the sun, in the inverse square proportion to the distance, and Borelli, who suggested, also without demonstration, that there was a centrifugal tendency in counterbalance with a gravitational attraction towards the sun, so as to make the planets move in ellipses. D.T. Whiteside has described the contribution in Newton's thinking that came from Borelli's book, a copy of which was in Newton's library at his death. Newton further defended his work by saying that had he first heard of the inverse square proportion from Hooke, he would still have some rights to it in view of his demonstrations of its accuracy. Hooke, without evidence in favor of the supposition, could only guess that the inverse square law was approximately valid at great distances from the center. According to Newton, while the Principia was still at pre-publication stage, there were so many a priori reasons to doubt the accuracy of the inverse square law, especially close to an attracting sphere, that without Newton's demonstrations, to which Mr. Hooke is yet a stranger, it cannot be believed by a judicious philosopher to be anywhere accurate. This remark refers among other things to Newton's finding, supported by mathematical demonstration, that if the inverse square law applies to tiny particles, then even a large spherically symmetrical mass also attracts masses external to its surface, even close up. exactly as if all its own mass were concentrated at its center. Thus Newton gave a justification, otherwise lacking, for applying the inverse square law to large spherical planetary masses, as if they were tiny particles. In addition, Newton had formulated in propositions 43 to 45 of Book 1, and associated sections of Book 3, a sensitive test of the accuracy of the inverse square law, in which he showed that only where the law of force is accurately as the inverse square of the distance will the directions of orientation of the planet's orbital ellipses stay constant, as they are observed to do apart from small effects attributable to interplanetary perturbations. In regard to evidence that still survives of the earlier history, manuscripts written by Newton in the 1660s show that Newton himself had derived by 1669 at proofs that in a circular case of planetary motion, endeavor to recede, what was later called centrifugal force, has an inverse square relation with distance from the center. After his 1679 to 1680 correspondence with Hooke, Newton adopted the language of inward or centripetal force. According to Newton scholar J. Bruce Brackenridge, although much has been made of the change in language and difference of point of view, as between centrifugal or centripetal forces, the actual computations and proofs remain the same either way. They also involve the combination of tangential and radial displacements, which Newton was making in the 1660s. The lesson offered by Hooke to Newton here, although significant, was one of perspective, and did not change the analysis. This background shows there was basis for Newton to deny deriving the inverse square law from Hooke. Newton's acknowledgement. On the other hand, Newton did accept and acknowledge in all editions of the Principia that Hooke, but not exclusively Hooke, had separately appreciated the inverse square law in the solar system. Newton acknowledged Wren, Hooke, and Halley in this connection in the scholium to Proposition 4 in Book 1. Newton also acknowledged to Halley that his correspondence with Hooke in 1679-80 had reawakened his dormant interest in astronomical matters, but that did not mean, according to Newton, that Hooke had told Newton anything new or original, yet am I not beholden to him for any light into that business, but only for the diversion he gave me from my other studies, to think on these things, and for his dogmaticalness in writing, as if he had found the motion in the ellipsis, which inclined me to try it. Modern controversy. Since the time of Newton and Hooke, scholarly discussion has also touched on the question of whether Hooke's 1679 mention of compounding the motions provided Newton with something new and valuable, even though that was not a claim actually voiced by Hooke at the time. As described above, Newton's manuscripts of the 1660s do show him actually combining tangential motion with the effects of radially directed force or endeavor, for example in his derivation of the inverse square relation for the circular case. They also show Newton clearly expressing the concept of linear inertia, for which he was indebted to Descartes' work, published in 1644, as Hooke probably was. These matters do not appear to have been learned by Newton from Hooke. Nevertheless, a number of authors have had more to say about what Newton gained from Hooke, and some aspects remain controversial. The fact that most of Hooke's private papers had been destroyed, or have disappeared, does not help to establish the truth. Newton's role in relation to the inverse square law was not, as it has sometimes been represented. He did not claim to think it up as a bare idea. What Newton did was to show how the inverse square law of attraction had many necessary mathematical connections with observable features of the motions of bodies in the solar system, and that they were related in such a way that the observational evidence and the mathematical demonstrations, taken together, gave reason to believe that the inverse square law was not just approximately true, but exactly true, to the accuracy achievable in Newton's time, and for about 2 centuries afterwards, and with some loose ends of points that could not yet be certainly examined, where the implications of the theory had not yet been adequately identified or calculated. About 30 years after Newton's death in 1727, Alexis Clairaut, a mathematical astronomer eminent in his own right in the field of gravitational studies, wrote after reviewing what Hooke published. that one must not think that this idea of Hooke diminishes Newton's glory, and that the example of Hooke serves to show what a distance there is between a truth that is glimpsed and a truth that is demonstrated. Bodies with spatial extent. Gravitational field strength within the Earth. Gravity field near Earth at 1, 2 and A. If the bodies in question have spatial extent, rather than being theoretical point masses, then the gravitational force between them is calculated by summing the contributions of the notional point masses which constitute the bodies. In the limit, as the component point masses become infinitely small, this entails integrating the force, in vector form, see below, over the extents of the two bodies. In this way it can be shown that an object with a spherically symmetric distribution of mass exerts the same gravitational attraction on external bodies as if all the object's mass were concentrated at a point at its center. This is not generally true for non-spherically symmetrical bodies. 4 points inside a spherically symmetric distribution of matter. Newton's shell theorem can be used to find the gravitational force. The theorem tells us how different parts of the mass distribution affect the gravitational force measured at a point located at distance r0 from the center of the mass distribution. The portion of the mass that is located at radii r0 causes the same force at r0 as if all of the mass enclosed within a sphere of radius r0 was concentrated at the center of the mass distribution, as noted above. The portion of the mass that is located at radii r0 exerts no net gravitational force at the distance r0 from the center. That is, the individual gravitational forces exerted by the elements of the sphere out there, on the point at r0, cancel each other out. As a consequence, for example, within a shell of uniform thickness and density, there is no net gravitational acceleration anywhere within the hollow sphere. Furthermore, inside a uniform sphere the gravity increases linearly with the distance from the center. The increase due to the additional mass is 1.5 times the decrease due to the larger distance from the center. Thus, if a spherically symmetric body has a uniform color, and a uniform mantle with a density that is less than 2/3 of that of the color, then the gravity initially decreases outwardly beyond the boundary, and if the sphere is large enough, further outward the gravity increases again, and eventually it exceeds the gravity at the color/mantle boundary. The gravity of the Earth may be highest at the color/mantle boundary. Vector form. Field lines drawn for a point mass using 24 field lines. Gravity field surrounding Earth from a macroscopic perspective. Gravity field lines representation is arbitrary as illustrated here, represented in 30 by 30 grid to 0 by 0 grid, and almost being parallel, and pointing straight down to the center of the Earth. Gravity in a room. The curvature of the Earth is negligible at this scale, and the force lines can be approximated as being parallel, and pointing straight down to the center of the Earth. Newton's law of universal gravitation can be written as a vector equation, to account for the direction of the gravitational force as well as its magnitude. In this formula, quantities in bold represent vectors, where F12 is the force applied on object 2 due to object 1. G is the gravitational constant. M1 and M2 are respectively the masses of objects 1 and 2. Vertical bar R12 vertical bar equals vertical bar R2 or 1 vertical bar is the distance between objects 1 and 2, and is there a unit vector from object 1 to 2. It can be seen that the vector form of the equation is the same as the scalar form given earlier, except that f is now a vector quantity, and the right-hand side is multiplied by the appropriate unit vector. Also, it can be seen that F12, F21. Gravitational field. Gravitational field. The gravitational field is a vector field that describes the gravitational force which would be applied on an object in any given point in space, per unit mass. It is actually equal to the gravitational acceleration at that point. It is a generalization of the vector form, which becomes particularly useful if more than 2 objects are involved, such as a rocket between the Earth and the Moon. For 2 objects, e.g. object 2 is a rocket, Object 1 the Earth, we simply write R instead of R12 and M instead of M2, and define the gravitational field G, R, as so that we can write. This formulation is dependent on the objects causing the field. The field has units of acceleration, and G, this is m/s2. Gravitational fields are also conservative, that is, the work done by gravity from one position to another is path independent. This has the consequence that there exists a gravitational potential field V, R, such that if M1 is a point mass or the mass of a sphere with homogeneous mass distribution, the force field G, R, outside the sphere is isotropic, i.e., depends only on the distance R from the center of the sphere. In that case, the gravitational field is on, inside and outside of symmetric masses. As per Gauss' law, field in a symmetric body can be found by the mathematical equation, integral of d, area, d, field E equals 4 grams enclosed mass in Gaussian plane, data, equals 4 grams, ENC. Hence, for a hollow sphere, field inside surface is 0, 0, field on surface is gm/rr, field outside surface is gm/rr. For a solid sphere, field inside surface, at a distance r from center is gm/r, and rest fields are same as hollow sphere. For a cylinder of a given radius r, even if height varies, its field is constant given by gm/rr. Problematic aspects. Newton's description of gravity is sufficiently accurate for many practical purposes, and is therefore widely used. Deviations from it are small when the dimensionless quantities /c2 and v/c2 are both much less than 1, whereas the gravitational potential, v is the velocity of the objects being studied, and c is the speed of light. For example, Newtonian gravity provides an accurate description of the Earth/Sun system, since where orbit is the radius of the Earth's orbit around the Sun. In situations where either dimensionless parameter is large, then general relativity must be used to describe the system. General relativity reduces to Newtonian gravity in the limit of small potential and low velocities, so Newton's law of gravitation is often said to be the low gravity limit of general relativity. Theoretical concerns with Newton's expression. There is no immediate prospect of identifying the mediator of gravity. Attempts by physicists to identify the relationship between the gravitational force and other known fundamental forces are not yet resolved, although considerable headway has been made over the last 50 years. See Theory of Everything and Standard Model. Newton himself felt that the concept of an inexplicable action at a distance was unsatisfactory. See Newton's reservations below, but that there was nothing more that he could do at the time. Newton's theory of gravitation requires that the gravitational force be transmitted instantaneously. Given the classical assumptions of the nature of space and time, before the development of general relativity, a significant propagation delay in gravity leads to unstable planetary and stellar orbits. Observations conflicting with Newton's formula. Newton's theory does not fully explain the precession of the perihelion of the orbits of the planets, especially of planet Mercury, which was detected long after the life of Newton. There is a 43 arcsecond per century discrepancy between the Newtonian calculation, which arises only from the gravitational attractions from the other planets, and the observed precession, made with advanced telescopes during the 19th century. The predicted angular deflection of light rays by gravity, that is calculated by using Newton's theory, is only 1/2 of the deflection that is actually observed by astronomers. Calculations using general relativity are in much closer agreement with the astronomical observations. The observed fact that the gravitational mass and the inertial mass is the same for all objects is unexplained within Newton's theories. General relativity takes this as a basic principle. See the equivalence principle. In point of fact, the experiments of Galileo Galilei, decades before Newton, established that objects that have the same air or fluid resistance are accelerated by the force of the Earth's gravity equally, regardless of their different inertial masses. Yet, the forces and energies that are required to accelerate various masses is completely dependent upon their different inertial masses. as can be seen from Newton's second law of motion, F equals ma. Newton's reservations. While Newton was able to formulate his law of gravity in his monumental work, he was deeply uncomfortable with the notion of action at a distance which his equations implied. In 1692, in his third letter to Bentley, he wrote that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity, that, I believe, no man, who has in philosophic matters a competent faculty of thinking, could ever fall into it. He never, in his words, assigned the cause of this power. In all other cases, he used the phenomenon of motion to explain the origin of various forces acting on bodies, but in the case of gravity, he was unable to experimentally identify the motion that produces the force of gravity, although he invented two mechanical hypotheses in 1675 and 1717. Moreover, he refused to even offer a hypothesis as to the cause of this force on grounds that to do so was contrary to sound science. He lamented that philosophers have hitherto attempted the search of nature in vain for the source of the gravitational force, as he was convinced by many reasons that there were causes hitherto unknown that were fundamental to all the phenomena of nature. These fundamental phenomena are still under investigation, and, though hypotheses abound, the definitive answer has yet to be found. And in Newton's 1713 General Scholium, in the second edition of Principia, I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses. It is enough that gravity does really exist and acts according to the laws I have explained, and that it abundantly serves to account for all the motions of celestial bodies. Einstein's solution. These objections were explained by Einstein's theory of general relativity, in which gravitation is an attribute of curved spacetime instead of being due to a force propagated between bodies. In Einstein's theory, energy and momentum distort spacetime in their vicinity, and other particles move in trajectories determined by the geometry of spacetime. This allowed a description of the motions of light and mass that was consistent with all available observations. In general relativity, the gravitational force is a fictitious force due to the curvature of spacetime, because the gravitational acceleration of a body in free fall is due to its world line being a geodesic of spacetime. Extensions. Newton was the first to consider in his Principia an extended expression of his law of gravity, including an inverse cube term of the form be a constant, attempting to explain the moon's apsidal motion. Other extensions were proposed by Laplace around 1790 and Descombes 1913. Laplace. Descombes. Solutions of Newton's law of universal gravitation. N-body problem. The n-body problem is an ancient, classical problem of predicting the individual motions of a group of celestial objects interacting with each other gravitationally. Solving this problem from the time of the Greeks and on has been motivated by the desire to understand the motions of the sun, planets, and the visible stars. In the 20th century, understanding the dynamics of globular cluster star systems became an important n-body problem too. The n-body problem in general relativity is considerably more difficult to solve. The classical physical problem can be informally stated as, given the quasi-steady orbital properties, instantaneous position, velocity, and time, of a group of celestial bodies, predict their interactive forces, and consequently, predict their true orbital motions, for all future times. The two-body problem has been completely solved, as has the restricted three-body problem.